It's probably apocryphal, but the story goes that Leonhard Euler discovered Euler's method when he was trying to help predict the motion of the moon through the sky. And the reason for this is because the position of the moon was thought to be a really good way to get an absolute time reference over the entire planet. At every location on the Earth, you can always, if you can see the sun, you can always tell what time local noon is. But that doesn't help you figure out what your longitude is. And this was important for navigation. Well, if you can locate exactly where the moon is relative to the background stars, it's going to be in the same place for just about everyone on the Earth at the same time. So it would give an absolute reference if you could figure out where the moon is. Well, that involves solving a differential equation. Okay, the differential equation is actually very hard to solve accurately, and at the time, no one had a really good method for doing that. So Euler's method would give an approximation to what the solution of that differential equation would be, and thereby should be able to predict the location of the moon. Now, as it turns out, using the location of the moon does actually work to help you give an absolute time reference and therefore find your longitude. The disadvantage is this happened about 100 years after accurate clocks that were portable came around and really illuminated the need for this kind of technique. But nevertheless, Euler's method works on many different differential equations, and although perhaps because of its problems that we'll talk about in this video, it shouldn't be used as the method of choice, it's certainly the easiest and quickest thing to code up that will give you some idea about where your differential equation solution is going. Oh, and yes, you can see the moon during the daytime. Euler's method is the essence of simplicity. If we want to solve this differential equation, this initial value problem, dy dx is equal to f of x and y of 0 is equal to some y naught, what Euler's method has us do is it has us rewrite the derivative, normally as a limit. Limit as h goes to 0, of y of x plus h minus y of x over h. It has us approximate that just by erasing the limit sign. So we're taking some fixed value of h, which is not going to 0. And the point is that we're going to say that this is approximately equal to f of x, y. And of course, this is y evaluated at x. Okay, solving for y of x plus h is not at all difficult. And this is indeed Euler's method. The point being that later values of y are determined in accordance from and predicted by previous values of y and, of course, x. So how do you use this? Well, it's best to think of this as in terms of a table. And the table has got values of x, it's got values of y, and it's got values of f. So let's see how that goes. Let's consider the following initial value problem. Y prime is equal to minus 5y with y of 0 equals 1. We happen to know what the solution is. The exact solution, you can find this by separation of variables or any other way you might like, is just e to the minus 5x. Now, if we try a very small h, because remember, really that h is supposed to be going to 0, so pick a small h, 0.01 ought to do the job. Something like this will certainly be enough to get the point across. So this is the table, and I'll fill out the rest of the table in green. Now this is in black is our given values. So our initial condition is the first row, and our x value is the first column. You can see that, okay, what is f evaluated at the first point? Well, the first point is just minus 5 times y. Okay, so the y is 1, minus 5 times y. The second entry in the second column is 1, that's the current value of y, plus 0.01, that's the h, times minus 5. That's coming from over here. Okay, so what is that number? Easily found, that's 0.95. And in fact, the exact value is 0.951. Just you can track the exact values as well. Normally you can't add this last column, but let me put it in there. That's a 1, that's 0.95. .90 and 0.86. Okay, those are the exact values. All right, so continuing along. So what do? Well, we want to fill out the next entry, so the third column, second row, this place here. That is minus 5 times the corresponding y value. So minus 5 times 0.95 gives us minus 4.75. Okay, now the next entry here is minus 0.95 plus 0.01 times the minus 4.75. Okay. And putting that into the handy-dandy calculator gives me 0.90 indeed. All right, well, great. Let's multiply 0.90 by negative 5 to fill in the F column. That's minus 4.5 and change. Okay, so what goes in that corresponding y then is 0.90 plus 0.01 times minus 4.5125. Okay, typing that into the calculator, I get minus 0.85. Pretty close. And of course, we don't need this entry here. Now, as you can see, there's a lot of arithmetic involved, but at least it's coming up with an approximation that seems to be tracking the exact solution pretty well. Well, if you're Leonhard Euler, of course, you've got to do this by hand. But if you're now in modern times, we could use a computer. Of course, there's the saying that, well, to err is human, but to really screw up requires a computer. That's a cautionary tale when it comes to Euler's method.
So as you probably can imagine, doing Euler's method by hand, although that's probably the way Euler did it, is very tedious and likely to make a mistake. So let's instead use a computer. I have this computer here, this PDP-1134. It will do just fine. So let's use it to simulate the solution to Euler's method for y prime is equal to minus 5y with y of 0 is equal to 1. I've written a small Fortran program that we can run on the computer and have it compute for us. Okay, there's the program. Let's save it. And let's compile it. And link it And finally, let's run it. Oh, that's not what I was expecting. So you'll see, there's our initial condition. This is 0, x equals 0. There's our initial y value. And you can see that it starts out, as it should, with y prime is equal to minus 5. But then, wait a moment, y should not be negative. And what's all this? What's all this garbage? Well, what that is that's actually the computer telling us the numbers are too big to fit there. Euler's method's got a problem when the step size is too large. So whenever you use Euler's method, you need to choose a smaller step size. So let's go modify the program with a smaller step size and try it again. So here's the step size. Let's make it run for quite a few more steps. Compile. Oops, I typed it in wrong, I can see. Compile, and link. And now you can see no problems. Even though we're going along just fine, the y values are decreasing nice and smoothly, the x values have gone up, and the y prime values go down too. So, lesson learned, whenever you're using Euler's method, take a small step size. This is why there are better methods that you could use a larger step size, but if you're going to use Euler's method, you need to use a very small step size in order for it to give you good results.